Recording has started, so you are now being recorded, so let that be known. And then the next thing I'm going to do is I'm going to share my screen, especially for the people online more than anybody. So if somebody online could maybe just let me know that you can indeed see my screen right.
Yeah, we can see it. Thank you.
Perfect. Thank you very much. All right, so I'm probably just gonna sit here because most of what I'm gonna do is gonna be in regards to some software that I'm gonna be talking about. I'm gonna silence my phone here real quick. All right. So just to introduce myself, my name is EJ Daigle. I'm the Dean of Robotics Manufacturing here at Dunwoody. I'm also the current president of the Twin Cities chapter of the ISA. In addition to that, what you may or may not know about me, I'm also a certified machine vision professional through the A3, which is the Association for Advancing Automation. Is what it used to be AIA, now it's called A3. So that's what it is. And so what I'm going to talk about tonight, these are some of the learning objectives I want everybody just to kind of see ahead of time here. We'll talk a little bit about the Certified Vision Professional exam. We'll talk about some of the very, very basics of machine vision. I like to use it isn't mine, but I stole it from somebody else many moons ago. The 25-bit pattern example. I think it's a great example for teaching pattern recognition in machine vision. It brings it down to kind of a really basic scale so people can understand why or how machine vision locates parts in space. We'll go over some of the machine vision components, a few machine vision applications. I'm going to show you how to set up the software. And the slides in here, or if you go back and watch this video later on, if you want to download the software that I use Cognex's Insight software as my primary vision tool. I've also used software from Keyence. I have a robotic snowplow team at Dunwoody. We're using a software called RoboRealm to guide our robots for HEV purposes. So I've dabbled in about 2 or 3 different machine vision softwares and even 2 different machine vision programming schemes inside of Cognex as well. So we'll talk a little bit about the software setup, and then I'll show 2 simple demonstrations using an emulator. And the reason why this software setup is pretty cool is if you go back and watch this video at a later time, or if you want to get more involved in machine vision and you want to go through the software and get it set up, the great thing the reason why I like the Cognex software a lot is it comes with an emulator, so you can do offline programming. So you can take a sample of, let's say you took 10 images on a machine vision camera, and you wanted to train those images. You had a good part, on the edge good part, and then you had a sequence of bad parts. The emulator, you could actually go through and train that without being hooked up to any hardware. So that's the beautiful thing, is it's software on your PC, you can run it. We've even done it with like webcams. You can do it, and it's pretty cool stuff. So, all right, so let's get into it here. So the first thing I'll talk a little bit about is the A3 certification. This is a certification we do with our students here at Dunwoody. Our students that are in the automation controls engineering program, it's the program Bob teaches in. They take a course in machine vision. And as part of that course, the final exam for that course is the Certified Vision Professional Basic exam. What's kind of cool about that exam, I'll show you here, is once you pass that exam, so this link here will link me to the exam. I may have to reshare my screen here real quick. Share it here. Sometimes I just want to make sure I'm actually hitting it. So this link here will take you to the A3. Used to be, formerly it was AIA. Now it stands for the Association for Advancing Automation. And so you come in here. What's neat about this is you can see all the certified vision professionals that A3 has certified. And there's a lot. I mean, there are a lot of them in here. So some names you might recognize, like, let's see here. This EJ Daigle character right here is one of them, right? Or Bob might recognize. Anjana is in here somewhere. There's a lot of them in here. But the neat thing about it is you can take a course through A3. It's an online course, and at the end of it, there's Anjana right there. She didn't put in any of her stuff here. But you can take that course, and then the culmination of that course online is to actually get certified, which is really, really cool. So let me get back out of here. I'm unsharing and resharing my screen 100 times here, so I apologize. There we go. And folks that are online, if for some reason I didn't share that, can you guys see that, Jonathan? Let me know if you can't see my screen. I think you can, because I see a little red border.
Yeah, we can see it.
Perfect. So here are some of the basics of machine vision. And and I apologize, I'm going to go really, really rudimentary here and take you down to really, really the basics. I can remember when the first digital camera I ever saw was a Sony, had a floppy disk on it. Anybody remember that camera? There was a Sony digital camera, and instead of using film, I think it was called the Mavica or something like that. And the digital camera used a floppy disk as film. And I thought that was the coolest thing in the world because I had hundreds of floppy disks, right? I felt like I had unlimited film, right? Mm-hmm. And it shot at like 640 by 40 is what it shot at. I mean, it shot at at a pretty low, it might even been lower resolution than that, to be honest with you. But it stored it on a floppy disk, because floppy disks were like 1.4 meg, right? So maybe you could get like 6 images or 4 images. I don't remember what it was stored at. It was really low resolution, and you could get a handful of images on a floppy disk. And you just carry around a stack of floppy disk. And now, all of a sudden, we're carrying around cell phones that are shooting at 10 megapixel, 15 megapixel, 20 megapixel, and you're storing hundreds of them. And in some cases, most of the time, not even storing them to your phone anymore. Now they're stored in the cloud somewhere, and you've got unlimited storage as far as what you want to store. Well, machine vision really wouldn't have existed in the aspect that it does today without digital cameras, like what we're talking about today. So the idea that we are taking an image and converting it into, basically it becomes just a sequence of pixels. Each one of these pixels has some RGB signature to them, so some color signified by them. And all we're looking at when we look at an image like this is we're looking at how many pixels can I get in the X direction and how many pixels can I get in the Y direction. So when we talk about 640 by 480, you can see exactly how many pixels are there. And what they're really kind of showing you here is they're showing you 3 different images, one being kind of cloudy and kind of murky and kind of low resolution, and one being fairly sharp on the right there. All of these shot at like a 4x6. If you were to print them out like a 4x6 standard picture size, one would be very clear and one would be kind of like you took it out of focus or something, right? But for machine vision, that's important to us because the number of pixels determines, where I can find the contrast of an edge, where I can locate a pattern. And so very much similar to what we would do with the digital camera, we also do with machine vision cameras as well. What I will tell you is we don't need the kind of resolution with a machine vision camera that we would need with the digital camera that you're taking your family photos with, right? Because traditionally what we're doing in machine vision is we're inspecting, we're looking at something. So if I'm looking at this water bottle that I see right here, and I want to verify that the water is at the right level, all I really need to do is find an edge, right? I need to find, or if I want to figure out that the cap is on straight, my cap is not on straight right now, all I really need to do is look at those edges and compare them to other features. I need a datum to compare them to, and then I can make that comparison. But what we're seeing here is greater number of pixels in that same space creates a crisper image. So some more vision basics here. So the binary, grayscale, RGB. In binary or monochrome images, the most basic of that is what we call binary, meaning each pixel can only be one of 2 states. It is either a 0 or a 1. It's either black or it is white. So the top image there, what you see is what you're going to see in a few slides here, my 25-bit example. And if I asked everybody in this room right now, what letter is that of the alphabet, you would say J. And everybody in here could tell us that, right? A machine vision system would have to be trained to recognize that. You would have to tell a machine vision system how to recognize that. Now, mind you, that's only 25 pixels, 5 pixels in the X direction, 5 pixels in the Y direction. And some of them are black and some of them are white, and we can determine what that might be based upon training. Versus a grayscale image, each pixel is an 8-bit shade of gray. where black is 0, white is 255, and somewhere in between is gray, 128. And then that just gets either brighter or darker as I go away from 128. So if I go in the negative direction from 128, I become a darker image. If I go in the positive direction from 128, I become a brighter image, a more white image. And if I eventually get to 255, that pixel is as bright can be, right? So it's going to be extremely bright. So I'm white all the way down to black, but now I have the ability to show gray. And in my little starburst example there, that's a collection of pixels, right? That's not a 25-bit image anymore, right? That's going to be a lot more pixels that we're looking at because we can see the shape of that S and it's not pixelated. And then color RGB, or red, green, blue images, are a triplet, an 8-bit triplet mixture of scaled red, green, and blue values. So if you look at the bottom of the slide here, if I had 25500, that would be a purely red pixel. If I had green, 02550, that's going to be a purely green pixel, and blue would be 00255. And it's the mixture of those colors, kind of like a painter with a palette mixing two colors together to create some custom color like you see down in the bottom right there, which is 215, 105, and 50. That's the color, kind of a orangish brown or something that I'm seeing there on the bottom right. My wife tells me I'm not very good. I'm colorblind. I can't tell. I'll say those socks are blue, and she'll be, no, they're black. And I'm not the best example of this here, but some more basics on vision. So each pixel has that unique number. So I think everybody in here has gone into like a Word document, right? You go into a Word document and you change the color of your font, or you draw in a little graphic, like a little box or something. You want to fill in the box with the color. And if you go from the standard tab on the right there over to the custom tab, now you can create any color you want, right? 255, 255, 255. And by changing those numbers around, I can get anything I want. So like on the example on the right here, my current color, I don't know what my current color was. It looks like I chopped it off here, but my current color was somewhere down in this blue, kind of bluish gray down here. And then my new color is going to be white. My new color is going to be white because I'm going to 255, 255, 255. That's how I know I'm white. And again, red, green, blue, and then black would be 0, 0, and 0. So I can create a whole slew of colors by doing this type of stuff. All right. That stuff is important. Now the 25-bit example, 25-bit pattern example. I use this in class to show students if you're looking for a pattern. So if you've got, in the world of machine vision, the camera is going to generate this search area, this region of interest where I'm going to look for something. I'm going to look for a pattern. That pattern is how I'm going to locate my part, because if I can't locate my part, I can't inspect my part. So I always use this as my good example of patterns. So imagine a set of 25-bit patterns. Each binary bit is either on or off, as indicated by a black or white fill. Similar to barcodes, machine vision systems require the elimination of noise to improve execution. And so like we talked about a minute ago, Bob said that one letter was a J, the bottom right's a J, but we can look at this B, O, C, T, D, G. And so why do you say that? Because we recognize these letters. We've been trained to recognize these letters from our alphabet, right? So we need to train the machine vision system to recognize the pattern that we're looking for. Now, the beauty is in a machine vision system, when it comes to characters, many of these patterns are already trained, right? So we have optical character recognition, we have barcode recognition. So we have a lot of things that are already out there that we don't have to train, but there's going to be some pattern training that we're going to do tonight to make this a little simpler. So machine vision system, no different than the human brain. We must cope with distortions and noise. If I showed these patterns right now, and I was showing them on a piece of paper, and I turned off the lights, would you be able to read those patterns? No. Machine vision systems are extremely delicate to lighting. I can give you an example. I worked with some of my graduates up at Boston Scientific up in Arden Hills. They have a battery line up there where they produce the batteries for neurostimulators, pacemakers, all these different things. And they have all these cells made by a company called Oak River Technologies, which is now part of PAR Systems. Oak River Technologies builds these cells. They're robotic automation cells. And what they do is they stamp out lithium. and they stack the lithium in these little metal cases, and then they fill that case up with an electrolyte, and that becomes a battery. So you can't just buy a Duracell battery for your pacemaker. You've got to get the battery from Boston Scientific or and there's good reason, right? You don't want your battery to go dead after 3 months. You want that pacemaker to run for 12 years, right? We want this thing to last a long time. But what they did was they had a long weekend at one point. And these cells are filled with machine vision, with automation, with a Scara robot inside of them. And what happened was they had a long weekend and they're going to shut down and do some maintenance. And it was the facility doing the maintenance. The facility was going to replace all the fluorescent tube lighting in the entire battery line with LED lighting. Great idea, right? That's less maintenance, lower cost on the energy bill. There's 100 good reasons to do that. They came in on Monday morning. They brought the system back up over a long weekend. They brought it back up. All of the cells went into air. All of the cells went into air. Why? They changed the lighting. So changing lighting in a machine vision system can be absolutely detrimental to the process. You've calibrated the system to a certain amount of ambient light. So what you'll see out in the real world is you'll see that people will they'll smoke out the windows. They'll put a dark tint on all the windows of the cell. The machine vision system will go inside and they'll illuminate that cell from inside the cell so that the ambient light is not part of that. As a way, we call that a doghouse in the world of machine vision. We hide all the ambient light and then we control our light from the inside. We can control the angle the light's coming in from. We can control the type of light and exactly what the light is. So in this particular example, if I had a 25-bit pattern, and I might say, well, the percent of match of these images shown, oh yeah, here's what we got. We've got our trained on the left. That's our trained image for a B. Now, what would you say? I mean, I think anybody in here would say, oh, I can recognize the one on the right is obviously still a B, right? I mean, that's pretty close. The one on the right here is still a C. I mean, that looks exactly like a C, doesn't it? However, it's shifted, isn't it? And the one on the right here looks like a D as well, except it's shifted. So out of these, when you train these and you get these images, and if you're marking off on these images, what you're going to see is that first one's got a 92% pass rate. Why? Well, because I can see I'm missing a pixel on the middle of the B here, and on the upper left corner, I'm missing a pixel on the B there. The rest of it looks pretty good. So only 2 pixels are bad out of 25. That's a 92% pass rate. The next one is a 60%. This guy's going to fail almost completely. Why? Because we are not lining up very well with any of these pixels. We are now below that 90% threshold, and now we've got a problem here, right? And the same on the last one here. A 92% pass rate again. We just got a couple pixels that are either off when they should be on or on when they should be off, whatever the case may be. So when we train a pattern, what we're really doing is if this is the pattern I'm looking for, this B, maybe I'm looking for it on a part, and that's going to orient my datum for that part so I can take measurements. If I can locate that B, then I'm good. But then I need to set a threshold for what's an acceptable location score. So if I didn't find the pattern with at least, let's say 90%, then I'm not going to find the part. I can't find the part, I can't take the measurement. Lighting will affect this. Something as simple as some dirt on the part, some dirt on the camera lens, anything like that can affect it to the point where you're not going to see your part anymore. So the components that make up the machine vision system, so obviously we have our camera and our lens. Those are 2 very, very important components. You combine that with the lighting, and those are your 3 critical components. The focal length of the camera, the distance to the part, the sensor itself that's inside the camera. Many machine vision systems that are out there, even when they're measuring color, they'll still use a black and white camera. They're still going to measure with a monochrome camera. And you might say, well, why the heck would they do that? They don't need a color camera necessarily. They can bounce light off of that, and the amount of light that reflects off of red is different than the amount of light that reflects off of green or blue or black or white, right? So we don't necessarily need a color camera to detect color. We can detect color using a grayscale camera. The monitor, which is typically optional, but the monitors can be nice to show what's going on. especially when you're calibrating the system. You want to look at the good parts and the bad parts and make a decision. You have some sort of vision processing. Nowadays, a lot of these cameras have a lot of smarts in them, meaning that a good Cognex camera, for example, the processing is all going to happen inside the camera. So some of our most state-of-the-art machine vision systems may have a separate processing area where processing occurs, but these cameras are super duper smart, and they're just going to send signals over Ethernet. That's all they're going to do. I can remember one of the first ones I ever worked with that had the smarts inside. It was like its own little PLC. It had inputs, it had outputs, and then the code I wrote based upon the vision sample determined what outputs turn on, what inputs. You know, I could trigger with an input, and then I could look at the part, say the part's good, and I could trigger an output, and I could send that somewhere else. Could be an output that just turns on a red light or a green light. Could be an output that turns on a pneumatic cylinder to reject a part off of a conveyor belt. It could be a lot of different things that I look at along the way. And then obviously what we're doing here is you can see down here is you'll see the light source, the camera, and the lens, and obviously the thing we're really looking at are the inspected parts that we're inspecting. That's what we're looking for there. So machine vision applications, this gets kind of fun because I'm going to show you an example of each one of these. So this is IoT analytics for machine vision report from 22 to 27. So machine vision applications, 46% of applications deal with inspection. So monitoring the visual appearance of an object for features, defects, or anomalies. So my example of a water bottle or my Diet Coke bottle, is the cap on it. Is the label on there? Are all the pieces there that I need there, right? Identification is 31%. So this can be reading date codes, barcodes, lot numbers, anything like that. That's going to be identification. So there's a lot of optical character recognition. There's a lot of barcode reading that happens in there. And every good machine vision system will have a barcode system built into it. So you don't have to have a separate barcode reader. You don't need to buy an expensive machine vision system to be a barcode reader, but an expensive machine vision system can be a barcode reader as well. Okay. And then guidance, provide the location of orientation of a specific object. So my son actually works for a company called Daigle Systems, and they do robotic automation all over the world, and they do packaging. So parts will be coming down a conveyor belt, and they may have 60 parts a minute coming across this conveyor belt. And they'll have robots that are picking up those parts and putting them in the boxes. In some cases, inspecting the parts while they're doing it. So in order to do that, the part never stops moving. It's very important that the robot can see where that part's going to be. It needs an XY location so it can grab the part while it's still moving. I'll show you a video of that here in a minute. And then finally is measurement. About 5% of the applications deal strictly with measurement, calculating distances between two or more points. Our geometric locations on objects. So if I want to determine, we've got some metal stampings or even those lithium pieces that we're putting into the can to become a battery. If I wanted to look and make sure those are the correct size before I put them in there, I could measure that part. Just like taking a caliper or a micrometer, you can do that with an optical measurement. Now, when it comes to measurement, it's very, very important that you have some sort of calibration to the system. So pixels must be converted into millimeters or inches or something. So we use calibration grids that'll go underneath that as a target, and then we can use that to actually calibrate the vision system to a unit versus just in the other three here. Really, I'm just saying, oh, something's there, something's not there. I'm reading a code or I'm guiding to a location. Measurement, it's important that we are calibrated to an actual unit. All right, so go through a few of these now. So the first one we talked about is inspection. This is a picture I took. I have one of my alumni. This is one of the cool things. I have alumni working all over the city right now, right? So this particular gentleman is working up at Upshur-Smith, just northwest of here. Upshur-Smith is a pharmaceutical company, and this particular vision is not a Cognex vision system, but this particular vision system is working on a blister pipeline. So these are potassium supplement pills, and they're coming down. You can see them in the left image there. These nice kind of oval shaped tablets is what they are. Notice the red bin underneath there. You guys see the red bin underneath there? So you'll see a lot of these tablets that may have been cracked. They may have been deformed. There may have been something wrong with them, right? So what this vision system is going to do is it's going to scan every single tablet. And you'll see on the right here, as far as blister packs that came through this, I don't know if this was a day or a week, or I don't know how, it wasn't a week. It was a lot faster than that. You see the blisters, there was a total of 19,688 blisters. Of that, 16,820 were good. The size errors was 307. They also sometimes get what? Empties.
Yeah.
So a blister comes through and all of a sudden there isn't one there, right? So if you buy your pack, if you go to the pharmacy, buy your pack of medicine and you're expecting what, 10 pills there, and all of a sudden there's only 9, you're gonna be kind of mad, right? And in some cases, if it's a antibiotic or something and you're required to take 10 doses, now you're missing a dose as well. So stuff like this used to be people, right? This where people had this job. People had QA jobs where it was their job to watch things coming down the line and make sure something wasn't missing. I wouldn't want that job either.
Yeah.
Shaking our heads in here.
Yeah.
It's definitely not a job. I don't want that job. But mind you, when we were doing those jobs, they were coming at us a lot less fast, right? Things were moving a little slower. Now these things are flying, so they can really take these pictures and do them really, really quick.
That was one question I had is, tell me a little bit about the speed. You talk about many components, lighting being very critical, the angle of the lighting, and the fact that you needed to control lighting. But you have said very little about speed, and I imagine that, most of the applications are conveyor belt. I mean, I'm assuming quite a few are conveyor belts. Things are moving. Like
Yeah, so Upshur-Smith, this one isn't running super duper fast, but it is processing each part essentially is a blister pack of 10 pills, right? So this is a pretty unique process, but this was moving. I don't know if they were doing at least 50 or 60 blister packs a minute. So about one of these blister packs a second is coming through. Now I was up at Delcor Systems last week on Friday, and some of the parts that they're doing are upwards of 200 to 300 parts a minute. So these things are moving as far as, so when you're seeing that, it goes so far as like up at Delcor, I'll show you the video here in a minute of one of them. What they had to do is the parts were coming so fast that they had to have actually multiple cells of robots. So the first robot's picking the first part, the second robot's picking the second part, the third robot's picking the third part, because one robot wasn't fast enough to move the parts from the conveyor belt over to the boxes. So, and then sometimes they even have queues where if they're waiting on a box or something, they might set them up on a shelf, just to make room so that stuff isn't falling off the end of the conveyor belt or something. So they really, really fly. So, and I saw one that was, I was down at a company, I can't remember the name of the company, but they made the hypodermic needles. And it was producing a million of those a day. 1 million hypodermic needles with 100% inspection. And so I went over to they had a red bin like this, at the hypodermic needle machine, right? And in that red bin, there must have been, I don't know, there must have been 600 or 700 of these hypodermic needles that had been rejected off the line. So I look at this and I'm thinking, wow, just imagine the waste, right? That thing is full of hypodermic needles. The waste is incredible. And the guy that's over there says to me, goes, yeah, that's like 600. Yeah, that seems like a lot. It's not a lot when you're producing 1 million a day. It's like, you have to put that into some sort of perspective as far as, okay, wait a second, I guess it's not a lot. Do the math on that. What percentage is 600 of 1 million? That's a pretty small percentage, right? So, yeah, so these things can fly. Another thing that we'll see, this is the same vision system at Upshur-Smith. I just kind of like this one to kind of look at another example at the exact same company here. In this particular case, they're actually reading the lot number and the expiration date. So when you get into medical device, when you get into pharmaceuticals, everything is tracked. I mean, there is 100% tracking on everything. If there's a recall on a medication, they need to know exactly what lot number, when it was produced, what the expiration, they need to know everything about that particular package of medicine. So they track everything. So literally there's a snapshot. They're getting all of this data, exactly when it came off the line, and it all goes into a database that they can store that. So it's some pretty cool stuff. This is the one I was going to show you. This is actually this is the line that my son did. Now this one's a little different too, in that you'll see that this conveyor belt has some lighting from below as well. Sometimes you'll see what we call dark field lighting, bright field lighting, or backlighting. Those are kind of the 3 main types of lighting systems you're going to see in machine vision. So backlighting is the part is sitting on a conveyor belt. I'm going to light up from underneath. So my part's going to look like a black. This is a technical term, and you're going to think it's not, but it is. In machine vision, one of the most impressive technical terms is a blob. That is the term that everybody likes to use. A blob is nothing more than a collection of pixels that are connected together. So just imagine like a blob of pixels, like a big black blob. That's the part we're looking for. So in a backfield or a backlight, you'll see something like this where if it was lit from below the conveyor belt, I would just see a black image in the shape of whatever this thing is. If I was at greater than 45 on bright field and lower than 45 on dark field, and what that means is more or less of the light is going to reflect back to the camera. So if I'm shining light at this part and I'm either high on the part or I'm low on the part, I'm going to reflect more light away from the camera or more light towards the camera, depending on the angle of my lighting coming in at it. Make sense?
Yeah.
All right. So let me show you this real quick, because this is kind of cool to watch. Let's see if I can play it here. Got a lot of sound here. Yeah, so what you're seeing is we are locating every one of those parts. Now the robot knows precisely the XY location as that and it's down in the conveyor belt. It's a pretty cool thing to check out there. By the way my kid gets this image, right? He takes his little new flip phone, puts it on the conveyor belt, puts it like this, and lets it ride down the conveyor belt with all the guns and numbers, right? And I said to him, why didn't it pick up your phone? Yeah, and I'm looking for a blob of this size and things over this. Of course, everything else. You know what I mean? So that's how we know to not pick that stuff up. All right. See if I can get away from that now. There we go. All right, then the last. So we kind of went through the first three there. Again, we have inspection. That's our biggest utility, right? Identification is really big as well. We get into a little less when we get into robot guidance or guidance. I don't have to listen to the sound every time there. And then a little bit less with measurement as well. So measurement, I always think of measurement kind of like a go, no go. I can remember going into like machine shops and they would always have these funky tools, right? Like a tool that one side of it had a green pin on it, and the other side of it had a red pin on it. And the green pin had to go in the hole and the red pin couldn't go in the hole. And a quality inspector would work on the line and they'd pull this part off. They'd pull, every 10th part or every 100th part off the line. They'd stick the green gauge in. It goes into each of the holes. They flip the gauge over, they'd stick the red gauge in. It can't go into each of the holes. And as long as that passes, that whole lot is considered good, or however many parts that was part of, right?
Yeah.
So that's what we call go, no. But we can do that with machine vision.
100%.
And we can do 100, we do every single one. We can do every single one. The only trick though is it's important that we are calibrated to units at that point. It's not enough just to take a snapshot. We do need to calibrate to units. So we need something that's going to allow us to calibrate to units at that point. And I've seen people, this isn't the way to do it, but I've seen people take a 6-inch steel rule and put it under the camera and calibrate to units that way. And that's a quick way you can get it just up and running. But then you do need some sort of calibration grid under there, so you are actually calibrating to the that you want. So in this particular case, what are some of the things that we might want to measure on this part? And don't pay attention to the green measurement utilities that they don't necessarily mean anything on this particular part. We might want to know the length of the part, right?
Yeah.
That might be important to us. I have no idea. Maybe this angle here is really, really important. Maybe the size of that hole, right?
Exactly, that's fine.
Yeah,
If it's for mounting, you want to know the size of the hole.
yeah, you want to know the size of the hole, and it can get a little tricky in that in this particular part, I can see the flat here, but we can see this as a stamped or formed part, right? So I can see there's also a bend, and part of this part's coming up at me. So when I'm going to use this in a machine vision system, we may want to take measurements on the flat here, but this is a little trickier here, right? I can't measure that hole from above. I either need some sort of 3D machine vision system, or I might have another camera shooting in from this side or shooting in from that side. So, because maybe I find out, hey, this hole on the bottom here on the upright, that hole is extremely important, along with everything else on the flat. Okay, well, then I'll just put in another camera just to read that other hole. So I can just get that other measurement so I know if I'm good or not. Does that make sense? Awesome.
Presence or absence of those features, would that be classified as measurement in the go, no go context, or would that be a completely different discipline?
I would normally call presence or absence inspection, as in I'm looking for presence or absence. But I would tell you that in the measurement side of the house, a hole not being big enough or not being small enough is a measurement. So in that case, a hole that doesn't exist, I guess, is still a measurement, right? Yeah, what you'll find though, is when we set that, we're gonna do this part here in just a couple of minutes, by the way, we'll build it. You guys will help me build it. The part's gonna fail first. So the part's gonna fail first. I would probably inspect this part, like, let's say those two holes that are green right now, that the measurement of the size of those holes is extremely important. The first thing I would do is I'd say, look, I'm gonna just make sure the holes are there. You know what I mean? So I'm gonna count the number of holes, and if the holes are not there, I'm gonna reject the part right off the bat before I take the measurement. Yeah, so I'm inspecting for presence, and then I'm gonna inspect for measurement.
Separately, usually?
I would do separately, yeah. Now, when I say separately, realize that this is gonna happen, right? This is gonna happen in one shot. I'm gonna get one image, and I'm gonna process it all at once. Yeah, so separately from the standpoint, there are two tools in my tool bag, but it's gonna be one inspection that does both things, right?
For the same manager.
For the same image, yeah. All right, so I'll talk about the software setup here. I'm not gonna do it right now. I thought, there's people might show up with laptops or something. It's not a big deal. But if you want to go back and watch this later on, if you go to the Cognex.com website and you install, if you go to their support section and you go to software, you can install Insight Explorer 6.41, and I think there's even a new one now. But you can install that software for free. You can install the software for 100% free. And the reason why you can install it for free is because it doesn't do you a hell of a lot of good if you don't have hardware, right? So they're saying, well, let me get you hooked on the hardware. You'll want to buy the software, right? That's the exact opposite thing as what Rockwell does, right? Get me hooked on the hardware, and then I'll pay you a ton of money for the software. So it's kind of the opposite business model there. But once you have the software installed, you can then open up the Insight Explorer. You can go to System Options Emulation. And then you can go back to the Cognex website, and you can get the Insight emulator key. This is the really cool deal. You'll see here when I work with it, it'll make you create an account. They'll get your email address, and then someone from Cognex will be bugging every month saying, hey, are you thinking of doing, a vision application? I'm here to sell you stuff, right? Yeah. But it's worth it. I will promise you this, it's worth it. And then you go into the offline programming reference, you get the Insight software value log, you hit generate key, and it's going to generate a key. So your software is installed. And now that you can go in here, you can hit generate key. It's just going to give you a code. So what it's doing is just making sure there aren't bots out there that are downloading the software and installing them all over everybody's computer.
Right.
So it makes you do a two-step process, kind of like when you, authenticate to check your email nowadays, like every once in a while it has a two-step authentication.
Right.
This generate key is what's going to give you the key to actually be able to use the emulator. And now the emulator's set up. And you might say, well, why do I care? Well, here's why you care. This is the cool part. So what I'm going to do is I'm going to do a demonstration. Any questions before I demo?
So you can actually say, for example, this is probably the best example. You want to make sure that the bottle of water is full to a certain level.
Yep.
You can do that.
We're going to do that right now.
All right.
Yeah, not only can we do that, we're gonna do that in about the next 5 minutes if all things go right. Yep. Yeah, exactly right.
Having a bottle that is not completely failed.
And what I would tell you is, if I look at this bottle right here, right, there's a lot of things that can go wrong, right? Number one is there might not be a cap. Well, I don't even want to put water in here if there is, if this piece is in here. Well, I guess the cap was on last, right? But I want to make sure the cap's on. I want to make sure the cap isn't, cross-threaded. I want to make sure the cap is sealing. Anybody ever? I bought a case of water one time, got it home, and I go into my trunk of my car, and there's water all over. Why? Well, one of these was leaking at some point or something. I don't know if it was a loose lid. I don't know if there was a hole in the bottle. The other thing too is when they sell these, they want their label on there, right? They want that Ice Mountain label on here with the barcode, because if they're selling them individually, they want to be able to scan them, right? So the Ice Mountain is going to be perturbed if their label is. So I'm just thinking the number of inspections on just my bottle of water, right? The fill level, the label, the cap, all this stuff. And you're not gonna buy a bottle of water if the cap is broken like that, right? You're gonna say, well, who's been tampering with my bottle? I'm not, so that's sitting in the cooler at Quick Trip. I'm not buying that one. 'Cause it looks like somebody's already drank out of it, right? So, all right, so what I'm gonna do is I'm gonna share my screen again. And let's go here. And so those folks online hopefully can see what I'm looking at right now. So this is the cool deal about the emulator. In the real world, I would be connecting to a camera. I love the Insight software, and I've programmed in. I've used LabVIEW's, I've used NI Vision. I've used VBAI, which is Vision Builder for automated inspection. I've used Keyence. I've used Cognex. I've used Cognex both on the Insight and on the spreadsheet side. So I've got about six or seven different. So Bob, this is my one specialty. This is the one thing I know a little bit about. What I love about this particular version though, is they do a really good job of, this is all you gotta do. Step 1, step 2, step 3, step 4. So if you look on the left side of the screen, it's gonna tell you exactly what you need to do. Step 1, 2, 3, 4. And so what I'm gonna do is get connected means I'm gonna do one of two things. If I was connected to a camera right now, like on a conveyance line or on that robot line that I showed you, I would click on connect and I would type in the IP address and I'd log into that camera. And then I could calibrate the camera. I could take some part images underneath the camera, I could do whatever I want to do. What I'm going to do though is I'm using the emulator. This emulator button will not be available unless you go through that process I showed you on the previous slide. Download the software, get the emulator key generator, do all that stuff, and so on and so forth. If anybody wants to go home and try this and you're like, I can't figure it out, I think I still have a YouTube video out there that walks you through it. So if you type in YouTube Dunwoody machine vision, you'll see me talking about how to do it. So the emulator is what I want. I want to do the emulator. It's the standard emulator. And more specifically, I'm going to go get an image. So get connected. That first step on the left there is what says, hey, you're going to hook up to a camera or you're going to hook up to the emulator. Okay. 99% of the time, I'm going to hook up to a camera. But right now, I'm going to hook up to an emulator. Then the next step there is set up image. So set up image, I could trigger it from the camera, right? I can trigger it with an external trigger. I can trigger it constantly. I can do all kinds of things. When do I want to take the picture, right? But what I'm going to do is I'm actually not going to trigger a camera right now. I'm going to load my images from a PC. And this is the beautiful thing about Cognex. When I click load images from PC, it's going to bring up all of these sample images. And they're not sample images that are just dumb images. These are the images that their customers have asked for. Can you show me how to do a bottle inspection? Can you show me how to inspect a metal bracket? Can you show me how to do this? So what I'm going to do is I'm going to go to bottle inspection. I'm going to hit OK. Hit OK again. And now guess what we just got? We got a bottle inspection. I'll call this Diet Coke because it looks like a Diet Coke bottle to me. But we didn't get the label or anything. We're gonna inspect for level. Now, when you go into the emulator, they give you all of these different folders with images in them. I think there's like 50 folders or more with different types of parts that you can inspect. Like when I first brought it up and I saw the bracket was up there, right? The bracket we're going to do in a minute as well. The first image in every folder is what we call our golden image. What does golden image mean? It is the perfect part, right? I wish every bottle of Diet Coke coming down the line looked exactly like this. Because if it does, then every bottle of Diet Coke coming off the line is perfect, right? So that's what we call our golden image. Now I'm going to scroll through these images real quick. And you guys tell me if you see any errors. If this is the perfect bottle of Diet Coke, that one look okay? It's pretty good. How about that one? Yeah. So the image is floating around. Now, mind you, that's also a problem. When people first started working in machine vision, they tried to aim the camera at the same location every time, and they tried to trigger the camera at the exact same spot. And what they discovered was parts don't always line up in the same spot. You know, when those parts are coming down the conveyor belt and the robot's picking them up, sometimes the parts are turned 45 degrees. Sometimes they're, and I'm putting them in a case and I want to stack them neatly. So that's all stuff that's important. How about that one? That one might be problematic, huh? How about that one? Yeah, so now we got a cap that's loose. How about that one? You can see all the different faults. So they gave you a handful that were good. And now I'm going to show you Look at the level difference between this and this and this. So this one appears to be a good part, but the level is actually lower than the golden image. See how close that is though? That's not a lot. So if you're down at the Pepsi-Cola bottling or the Coca-Cola bottling, this is the type of stuff they'd be looking at, right? They'd be looking and say, oh yeah, that looks good or that doesn't look good. All right, so let's go ahead and start an inspection of the part. So we got our images. So got connected to the emulator. We would get connected to a camera, and we'd be doing the same thing if it was a camera. I'd just be looking at a live image of different parts, right? I'd be putting a good part, a bad part, so on and so forth. Now I'm going to locate the part. It's important to locate the part because I can't take a measurement. I can't look for something if I don't know where to look, right? So that's an important thing that I have to do. So there's all kinds of cool tools. Cognex has actually patented and trademarked some of these software tools that they use, which is really, really cool. So you'll see like PatMax Redline and you'll see PatMax Pattern. They got some really cool tools. I always tell my students, we're going to use the most basic tool. And they're always like, well, why do we got to use the dumb tool? Because if you can do it with the dumb tool, you can do it with the easy tools, right? The dumb tool is going to be the most difficult to do it with, where some of these very advanced tools, it'll just do it for you, right? So what I'm going to do is I'm just going to use their most basic pattern tool because I might get into an industry where there's a camera that's 10 years old that doesn't have PatMax Redline on it, or it doesn't have PatMax on it, but it has pattern because pattern's been around for 30 years, right? So I'm going to go to pattern. And now what you have is you have two things up here. You'll see a green box and kind of a purplish pink box, right? The green box represents the search area. Where do I want to search? Now, if you can make the search area smaller, you will process quicker, right? You can get the picture quicker, you can process quicker, you can do all that. But when I was rotating through these pictures, one of the things I saw was that bottle doesn't always hit right in the middle, does it? That bottle kind of bounces around, doesn't it? So I want to make sure I'm always able to get the bottle. That bottle always has to show up in the green box or I will not find it, all right? The second box is what I'm going to model. So what I'm going to model is I'm going to model what that cap looks like. I'm just going to take a little image of that cap. I want to take enough of it, maybe something like that. And the good news, I don't know. What I'm really doing is I'm creating a datum. What a datum is like when a machinist wants to measure a part or they want to put it into a vise, right? They need a fixed jaw that they can smack it up against and they can make a measurement off that part, right?
Yeah.
Or a fixed part which they can indicate their vise on, and then they got a precise measurement how far over they've gone from that, right? So I want to create a datum. So what I'm doing is I'm saying, look, this is my datum. Every part should have a cap, and every part should have a cap with a little 90-degree bend in it. I'm going to use that as my datum, all right? I always am looking for something distinct that doesn't change. Like the level changes, so that angle and stuff might be different. The cap pretty much always looks the same, except if the cap isn't there, or if it's broken or something, then it might not look the same. Now, by clicking OK right now, as soon as I do that, do you notice the little green crosshairs? So a couple of things. Down in the bottom right, you'll actually see the image I'm going to use as my location pattern. Remember when I was talking earlier about the 25-bit patterns? And I need a certain percentage for me to find the part. So that's the image down in the bottom right. That's the image I'm looking for. And I can set in, you know, what's a match for that pattern and stuff. Yeah, I can do a score. I can put the accept threshold right now is 50%. So it just has to look close to that. It has a rotation tolerance right now of 15 degrees. So even if it comes in 15 degrees off, it'll still find it. Okay, fine. It is what it is. But really the test of this, here's the test of this, is I look at those little green crosshairs now, right? That is my datum. That's my datum. That's kind of my center of gravity for that image that I'm using as my pattern. As I scroll through these images, I want that little green crosshair to rotate around with the cap. So watch what happens. Did it stay with the cap? Did it stay with the cap?
Yeah.
So what that means is when I see that that thing is staying with the cap, there's your 15 degrees of rotation. It still stayed with the cap, didn't it? I like this because it's staying with the cap. My location tool is working perfect. I love my location tool. Sometimes you have to change it. Sometimes you might have to locate off the right edge, the bottom edge. You never know. Now, there is one in here. Wasn't there one with no cap? No, there wasn't. Okay, I guess I'm okay then. If there was one with no cap, you wouldn't locate the part and you would fail it. Well, that's okay, right? If there's no cap, I want to fail it anyways, right? So that to me is not a big deal. So step one, locate part, we're done. We got the part located in space. Now that doesn't tell me if the part's good or bad yet, does it? The next thing I need to do is I want to inspect the part. Now you might say, well, the most important thing in the EJ is that there's that's a level. We were talking about level. Can we do the level? We're gonna just discuss the level. Can we figure out level? Well, if I don't locate the part, I can't measure level. The reason why is if I took a steel rule and put it up on the image here, and I said, oh, the distance from here to here is correct, and then I didn't move the steel rule, and the part moved, I might not even be on the part anymore. So that's why that location is so important, right? Everything's going to be based upon that as my starting location. That's kind of my origin for all my measurements, right? It doesn't matter where I put it from there, but I need to have an origin to start from. So next thing I'm going to do is I'm going to inspect the part. So I'm going to go down to inspect part. And under inspect parts, I'm going to go to, what do you guys think? Presence, absence, measurement, counting, identification, geometric, math, and logic. What do you think? If I want to know the level, measurement and distance is what I'm going to pick. I'm going to double click, and you can read about these when you go in here. Measure the distance between any two features, edges, circles, patterns, or blobs. Report the distance in pixels. So what I'm going to do is I'm going to double click on the distance tool, and you'll notice what it's going to do. The distance tool is going to bring up every edge it finds. It's going to say, hey, look, I see an edge here, I see an edge here, I see an edge here. Now, what I can kind of tell is when I look at a bottle here, there's like this little, like this little shoulder. Do you know what I mean? All the bottles have that little shoulder, even if the cap is screwed up, right? They all still have that shoulder. Because hopefully whoever's manufacturing my bottles has already inspected my bottles before they've come to me. So I don't have to worry about the bottles being bad. I just got to worry about filling them and putting a cap on them, right? So I'm going to use that little shoulder, which is kind of like right here. And I think I can zoom in here too. I'm going to use that little shoulder, which is kind of right here. I'm going to go down. Now this is where it kind of gets kind of funky. I'm not too concerned if I use this because we're kind of getting a 3D image here, aren't we? We're getting the back edge and the front edge of this liquid level. I'm going to go to the front edge. The only reason I'm going to the front edge is I feel like the back edge being further away, it's a little more distorted. It's a little bit distorted by the plastic itself. I'm getting kind of a lens effect on it. I don't like it. But what the beautiful thing is, notice on the right-hand side there, by just configuring that tool, the first tool I have up there is, of course, my pattern tool. That's the one that located the part, right? That located the part. The next tool was my distance tool. My distance tool requires two edges. So I clicked on one edge, I clicked on the other edge, and it's giving me the distance between there in pixels. Now, do I need to calibrate that to units? I don't care what the units are. Pixels are a great unit for me, right? What I care about is that I can detect between something that is obviously full and something that is obviously underfilled. That's what I really want to be able to detect right now. So what I'm going to do is I'm going to scroll through the rest of my images. So I'm going to zoom out a little bit. Yes, yeah, good call. So the range limits, and I don't remember if like a plus minus 10% is what they give. Yeah. So yeah, you can see that they're measuring that distance in pixels, and they automatically set a limit for me. They said, well, let's go up to 194 and down to 175. But yeah, you could make it whatever you want. You could say, I want really tight. I want 183 to 185, But I'm just going to see by scrolling through kind of what is it actually going to do, right? I'm going to go to this one. That one passes. See all the green dots on the right? That one passed. Oh, that one went out. Now take a look here. This goes right back to your question here, right? 189. My range limits right now on the high end is 194.156. And all of a sudden, this one failed. This one looks good to me, doesn't it? So this is it's probably a little bit different, but I mean, it's off by like, 0.1 pixels, right?
Yeah.
So this is where I might say, you know what? I'm going to make my range go up to 200. And I'm gonna make this bottom range go down to 175 or something, right? Now you'll see all of a sudden that I did that this one is in spec. How about this one? Now the great thing, right, is if it doesn't find that other edge, it's gonna fail it anyways. And I want this one to fail, right? So who knows, the level could be lower than this, but it's obviously gonna be too low. So I want this one to fail.
So if you didn't have the cap, it would have failed anyway,
It
right?
would have failed without the cap as well. I think let's see what happens because there's a cap that was cross-threaded, right? Let's find out what happens to the cap that's cross-threaded. So here's one where the cap is up and the little other piece is down, and it looks like it's failing. Now, I don't think this is failing for the right reason, right? So this is a little bit problematic because it's kind of failing for a bad reason, but I like it. It's not finding that other edge. I could, mind you, I could expand this down here. I'm not gonna, but I could expand that down there. This one here seems a little trivial. This is passing. That seems like a bad one right there, doesn't it? That's one I don't want to pass. And then let's keep going on. This one, was this my, well, that's my underfill. So I'm not a big fan of that one either, am I? Because that one there, what is it measuring? Why is it meant? So 184, 197. So that thing that I fixed earlier,
A little bit too far.
I went a little bit too far, right? I probably could have gone up to 195 or something, and I would have failed that one. So now I just want to kind of go through, you know, these are my common errors. Look, that one fails, that one should. That one fails, that one should, but not for this reason. That one didn't fail, but I think I can find that a different way, right? That one failed and that one should because it's too deep in pixels, right? So you're like, okay, this is working pretty good. Now the one I'm struggling with a little bit right now, I'm gonna make this one pass, even though we really don't want it to pass. So don't do stuff. I'm only doing stuff like this because I want to confuse you guys, but this one, if for some reason I made this image, right? I was like, oh, the level's passing. The level looks good. Well, it may, but there's a different problem here, right? The only reason I did that, why I expanded that up, is I want this to fail, but not for the level. I want this to fail for a different reason. Right? So what I'm going to do is I'm going to say, well, what else could I look at if I wanted to inspect this part and get this to fail? Well, one of my easiest ones to look at is to do what's called a blob count. So underneath the counting tools, you can count blobs. Remember I said this great, cool technical term that you guys are learning tonight? Blobs. They're just clusters of pixels, right? Counts the number of groups of dark or light colored connected pixels called blobs present in a region of interest. So I'm gonna click on this blob tool and I'm gonna say, you know what? I want to count the number of dark blobs in this area. And now, mind you, this is going to move around, right, with my tool with my pattern tool that I created. So it's going to move around with the cap. And what I'm going to do is I'm going to hit OK. That's where I'm going to look. And right now, what do you see for a blob count there? 1. That's what it should be, right? 1. Now, the other thing you can do under settings is instead of having either for blob color, I always say if I'm looking for black blobs, create black pixels. Set it so it knows what. And then your range limits again. Our range limits for this, I'm expecting 1 cap. I'm not expecting 2 chunks of black blobs, right? So now as I go through here, don't look at level right now. Level may fail because I just moved it up just to kind of get the one to fail for a different reason. But you can see 1 blob on the right here, 1 blob, 1 blob. What happened to the blob count there? 2 blobs. So what it's saying is look, and you can zoom way in on this thing. And what you'll see is the number 0, that's blob element number 0 or blob index 0, and blob 1, which is blob index 1. There are 2 distinct blobs. I really wish they'd number them 1 and 2, but as everything else in computers, 0 is a number, and we do consider that the first index, just like we do on a PLC output. 0 is an output number. So now I'm like, oh wow, that actually worked pretty good. And I don't know if my levels are still, that one's still kind of bad, huh? But pretty much that distance should fail. pretty much everything else is detecting. So you could spend, mind you, what we just did, you know, there's people that literally make a living setting up inspections like this, you know, and going out to the site, lighting it up, communicating. Because the next thing I would do, and why Cognex is such a powerful utility for what we do, is when you work in like the world of PLC. So if you're working with a Rockwell controller, an Allen Bradley controller, Cognex has add-on profiles that directly embed themselves into your Studio 5000 or your RS 5000 code. What that means is when I add the add-on profile for whatever camera I'm using, the PLC actually thinks it's a module within the rack. So all the I/O is communicated right across between the PLC and the camera. So if the camera sends a bad result and I want to use that bad result to have a pneumatic cylinder reject something off the line,
Right.
bam, I can use that inspection result as an input to the PLC. That's a huge, huge deal.
You use it like any other sensor.
Like any other sensor.
Okay, so that part and executive action is knock it out of the conveyor.
You got it. You got it. Versus like what we used to do back in the day. I'm going to show you another picture from Upshur Smith here. You know, what we would do back in the day, and this still works, by the way. Let me see if I got a good Upshur Smith here in here. Do somewhere. There we go. There's a really good one that I like in here. I'm just going to, and folks online, I'll share this as soon as I find it here. Give me 1 second. Come on. All my Upshur Smith images here. So I really like this one right here. Let me unshare and share. This is a great example of back in the day. This might even have a date on it. Let me see. It doesn't have a date on it. This picture is probably about 10 years old up at Upshur Smith. But what they were doing here was they have a couple of little sick through beam sensors here, right? So basically we're shooting a beam on an emitter and we're receiving it on the other side.
Okay.
What they've essentially done is they said, look, I'm going to shoot a beam across the top of this pill bottle. And if that lid isn't screwed on all the way, it will not clear the top of that lid, right? If it doesn't clear the top of that lid, guess what we do? We use this pneumatic cylinder to kick it off the line, is what we do. So really, in this particular case, there's no smarts required here. I don't need a PLC. If this thing, I can use I could have a normally open and normally closed bit to this thing. And if it changes states, I can use that bit to kick this off the line without even having a PLC interface, right? But now what I could do is I could actually take a camera and do the exact same thing. I could inspect for that. I could inspect for the label. I could get the lot number. I could do all of that in one inspection and eliminate the need for that. It's going to be a much more expensive sensor. However, I'm going to get a lot more value out of that sensor too, right? You got it. And so that's kind of a cool deal that you can do with this. Let me go back to Cognex. And the last thing I kind of like to do that I think is kind of fun. So I've got 2 inspection results, right? So the other thing you can do, and you'll do this in the emulator, it's kind of weird because I don't have any I/O, right? So like with my students, what I'll do is I'll say, hey, let's go down to the plot tools. And you might have a screen. Like I said, the screen is optional, right? You know, but I'm going to do I'm going to plot a string. I'm going to plot a string on the screen. I got to double click on it apparently. There we go. Now it came in. And then I'm going to locate that string. You'll see it's kind of where the little green crosshairs are there up at the top. So I'll locate it in the X direction, 100 pixels. I'll locate it down the Y direction, 200 pixels. And then and maybe I'll go a little bit deeper in the Y direction. I'll go down to 400. So now my little plot tool is going to be right here. And then the string I'm going to plot, this is where some of your old school like Visual Basic programming and stuff comes into handy, right? You can go into the string tool now and you can say, oh, I want to do let me think here real quick here. String. I do, I think I can just start typing. If, what was I thinking? Code. Logic, here we go, logic. Let's do if, there we go. I'll do the if, and then I can go into this if statement, right? And I can say, I can go right from my tools that I have over here. See the tools on the right-hand side? I can say, okay, if the the blob count tool, if that passes, so if blobs 1 passes, and I do my double and, so I'm doing a logical and is all I'm doing. So if blobs 1 passes, and I want the distance tool to pass as well, right? That'd be the other thing I want to pass. So let's go to distance, and distance, I'm in the distance tool, and distance 1 passes. Then I'll put a comma and I'll put in a string called pass, or I'll do a comma else, which will be a fail. So if this, else that type deal. So it's a nice little conditional statement that I'm gonna throw in there. I hit enter. One thing I want to do is, just because we ain't gonna be able to see that because that thing is so small right now, we'll go down and make this thing kind of big, and I'm gonna make it a funky color so we can actually see it. Oh, you can see it on the bottom, right? You can see the pass now. And as I scroll through these things, I get pass, 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 fail, fail. For a different reason, pass. We still would have to fix this one. I didn't take care of this one. And actually, I could take care of this one. If you remember when I did my pattern tool, I said what rotation was allowed, it was like 15 degrees. I could go into my pattern tool and lower that down to 10 degrees. I might just do that just to play with it. But anyways, so there you go, pass, pass, fail, fail, fail. So now all the ones that I'm expecting to do something are doing something. I'm just gonna see if I can, how quick I can fix that. See if this one fails. Oh, that failed, but I don't know if that failed for the right reason. It's not the pattern that's failing. It's something else. So I would probably have to do another inspection of some sort to get there. So what do you guys think? Pretty cool? Pretty cool. I'm gonna do one more quick inspection. I don't want to waste all time measuring Diet Coke bottles. So we're gonna do one more quick inspection. I'm not gonna save it. I'm just gonna go to a brand new job. I'm gonna clear all the data from that one and jump into a brand new one.
And EJ, that can be done, like you said, at fast speeds. This is.
Absolutely.
Okay.
Yeah, absolutely. This camera can, and mind you, the quality of the cameras get better every year, right? So you can, what was a $7,500 camera 10 years ago is now a, $1,500 camera, and it still has smarts on board. I mean, these things, they vary, and mind you, that if you want color, if you want 3D, you're gonna pay a lot more money, right? If you want IO on board or something like that, you're gonna pay a lot more money, but you might save money because you might not need a PLC. If you're just creating an inspection station that's going to accept and reject stuff, maybe it has a little gate arm at the end, and the good parts go off the end of the conveyor belt and the bad parts go into a trash can, right? Just using a little gate arm. I don't need a PLC for that, do I? I could do that with just a vision system that has a camera with one digital output on it.
Yeah. What do you do on things? I mean, just to follow up on an example, if you wanted to look at turbidity or acid with the liquid, if you were concerned, for example, it's, I don't know, you have, let's go, it's Diet Coke. So you're not expecting it to be clear.
No, so I could though, right? I could look at an area of a part and say, okay, is the light reflecting off of that in the manner I expect? So like if I was, I don't know, inspecting like bottles of Caribou coffee or something, I see these cold coffee that they bring into like, and it's kind of this weird color, right? It's kind of like a chocolate milk type color. You guys know what I'm talking about?
Yeah.
You see it in the stuff. You might say, God, we can look at that. We can know something's wrong based upon the color, the reflection of the light coming off of that liquid inside that glass bottle, right? At that point, you might use a color inspection tool or something like that and say, okay, I'm looking for a certain range of color, right? I've also seen where there's a bakery up in North Metro here where they have a camera above these croissants going into boxes. What they discovered was if they send out a box of these clear like clamshell things of croissants, there's 12 of them in this little package, right? If they send one of those packages out where one of those croissants is burnt, one of those croissants is cracked or broken in half or broken in any way, shape, or form, guess what happens to that entire box? It doesn't get bought. It sits on the shelf and it doesn't get purchased because people look at the box and they say, oh, that's a cruddy one. They put it back on the shelf and they grab the good one, right? So by putting one bad part into a case with 11 good parts makes 12 bad parts, right? It's like the rotten apple spoiled the bunch type deal. That's exactly what happens when you do something like that. So
Line one time where we were doing glass for touchscreens.
Mhm.
And I forget how we lighted it, but we had to recognize the glass so it could be picked up by a robot.
oh yeah,
And
oh yeah.
the glass was coming out on a conveyor belt after being washed. And I don't remember what we did, but somehow or other, we got the lighting right so it could recognize the clear glass.
That's a tricky deal right there, because you're talking about clear now, right? Something that's crystal clear, and you're right, that angle of that light can become very, very important. Or what's underneath, what's the color underneath that light or underneath that glass, that, whether it's the conveyor belt itself, the color of the belt, or if we're backlighting from below or something like that. So I don't want that project. That project sounds difficult.
It was.
The Diet Coke sounds a lot easier than that. Yeah. The other thing you can do with glass though too, right? You don't have to use a vision system to do stuff, right? Like if I have a capacitive proximity sensor, so like an inductive proximity sensor, I have to have a metal part as the target, right? But in a capacitive proximity sensor, I could have wood, I could have glass, I could have plastic, and all of those would trigger that part. And so the leading edge of that piece of glass could trigger a capacitive proximity sensor, and I'd get a similar deal. All right, I'm going to do one other. I'm not going to spend a lot of time on it because I know we could do vision all night long, and I'd be fine with that, but I don't know that everybody wants to do that.
Does that mean capacitive proximity sensor, passive prox sensor does not work with like?
Or absolutely works with metals.
It does.
Yeah, so capacitive proximity sensor is still calibrated on a mild steel target, just like an inductive prox sensor is. But a capacitive prox sensor will measure plastic, it'll measure wood, it'll measure all kinds of things that the inductive prox sensor just can't deal with. So inductive, you're gonna have to have brass, steel. You might be able to do aluminum with an inductive sensor, but inductive sensor is kind of like trying to create a magnetic field, right? You're disrupting a magnetic field with metal. You're not disrupting it with plastic or something like that. Capacitive you do though. Yep. I'm not a sensor guy. There are some sensor guys. Like you up to Banner up here in the West Metro out here. Oh my God, they got some incredible stuff going on over there. They can do some. So here's that other part that we looked at. I'm just going to bring this up real quick. We're going to scroll through the images real quick, and you guys are going to help me. You're going to build this. You're going to build this inspection, and we're just going to do a simple one. So we just got a few minutes left. So this is my golden part. Let's say that that's the problem we're looking for. What is the problem we're looking for? We're missing a hole, right? So for whatever reason, every once in a while, the die that punches these out, for whatever reason, I don't know why, it just doesn't punch that hole out. No idea why. All right, so I go through the rest of these. You'll see there's all kinds. Sometimes it's that hole, sometimes it's the other hole. I think somebody had fun with Photoshop as they're creating these images, right? But you can see that they stupid hole. And then they do stuff like this where they try to make a messy image and stuff. We're not going to deal with that right now. But what I want you guys to do is, here's what we're going to do. If I was going to try to just inspect for the hole and say it's good or it's bad based upon either having two holes or not having two holes, what's the first thing you need to do? Before you can do anything, watch what this part's bouncing around, isn't it? It's moving around in my space. I need to locate the part first. So I'm going to go to locate part, and we need to select a piece that's I don't know, it's geometrically unique, something that's going to help me locate this part in space, right? It doesn't have to be completely geometrically unique, but I almost am always looking at like a corner or something like that to locate my part off of. So what do you guys like for location? The green represents where I'm going to look, and I want to make sure this green box goes out far enough as well, right? And make sure that goes out far enough that I can see the whole part. So I'm not going to miss the part, right? But what am I going to model off of? I love it. I'm going to model off it right there. Yeah, to me, that's perfect. It's unique. It's kind of, it's always going to clock the part for me, isn't it? It's always going to clock the part. It's going to give me a datum from which everything else can be measured. I'm hit OK. And now the way I can test that is scroll through your images and do those little crosshairs that we just created. Do they rotate around with that image? Well, you guys really clocked it nice here because see how they're right in the middle of that hole? So we can tell that thing's staying right where it's locating the part every time, isn't it? That's a really, really good locate. Even when it's like way off angle, it's still locating it. That's perfect. All right, so we clocked the part. We created a datum upon which all of our measurements can be created now. Now we're going to inspect the part. And you guys get one option here. What are we going to do to determine if there's two holes or not? We've got measurement tools, counting tools, identification tools, geometry tools, and nothing below that do you want. Identification, let's see what's in identification. We got barcodes, postal codes, patterns, probably not. We could look at measurement tools. We could measure the distance between two holes.
How about count the blob?
Count the blobs. Somebody online did that for me. I love it. Very nice. Count the blobs. So there we go. We're going to count the blobs. We're going to use a rectangle to count the blobs. We're going to move this guy in here. We're going to say, okay, I'm going to look from here to here for a couple of blobs. I'm going to make sure my setting, it's only 2 and we want black blobs, right?
Yeah.
So my range limit is 2. And you are correct. My maximum is going to be 2 and my minimum is going to be 2. Everything else will fail. I really liked somebody online jumped in. That was awesome. And so now I got, what's that?
Could you do 4?
Could I do 4 blobs?
Yeah, you got 2 holes above.
So you could actually, so what you would do is in your settings, you may have to define the blob area because you might be looking at smaller blobs and bigger blobs, but you actually could, Bob. You could look for all 4 holes at the same time, or you could do 2 sets of 2. Look for small holes up here and big holes down here if you wanted to. Let's roll through this here real quick. So I got green is good, red is bad. Why is red bad? Missing a blob. Green is good, red is bad, green is good, red is bad. Just like that, you created the perfect inspection tool to count those blobs, and it worked like a champ. Pretty darn good, don't you think? All right, so questions for me. What did you guys think? An hour and a half of your life you'll never get back.
Pretty cool.
Pretty cool?
So you're paying the big bucks because of the software they built in to find the blobs.
Yes, yeah. So Bob's got a good question there. When you're buying these Cognex cameras, essentially the money is going into the tool, right? And it's less of a, honestly, the money is in the software, right? It's the software that somebody has developed that allows you to quickly set up a machine vision system and make this work, is what it really is. You know, versus people had to engineer this from scratch in the past, right? I'm going to take 2 sensors, I'm going to emit a light and I'm going to receive a light. And if that cap is off a little bit, it's going to break the beam and it's going to kick it off. So question.
Does the camera act as a self-sufficient sensor in this case where it runs whatever algorithms or machine learning models, it runs those at the edge?
At the edge.
No, there's software that's maybe on a PC or in the cloud or something, but then there's software that's actually running on a machine learning accelerator or something on the camera edge. Is that what we're looking at here with the Cognex?
So probably not the model I just showed you, but so Cognex has a whole line now that they call deep learning. So they call it deep learning, they call it machine learning. And I think that's what you're getting at there, is to the point where the system is capable of learning and making decisions that are more process oriented. I don't know if I can give a good example here, but it could be such that, I mean, my example will probably be silly here, right? But if the system is looking at parts, right? And so we were talking about that liquid level or whatever, right? And over time it sees a trend. It's not out of spec, right? It's not out of spec, but all of a sudden it's trending. It's saying, hey, I'm going down by a couple milliliters, every time I'm inspecting a part. So what I'm going to do is I'm going to tell the system that we got a problem. The system's going to make a change with no human interaction to actually add 2 more milliliters or whatever that system is to kind of learn, what might be going on. Or even in the case of inspecting parts, let's say that die that's punching out the metal stamp part, right?
Yeah.
Over time, it sees that those holes aren't quite the same size. They're still in spec, but they're just a little smaller or just a little bigger than they should be. Now I've determined, that tooling may be starting to wear out, and I'm going to do an auto tool change at some point or something like that.
So I guess wrong about the model, the machine learning model in this case is not running at the edge. There's no deep learning accelerator.
Not in this one.
On the camera.
Yep.
Where is it then?
So Cognex has a whole setup, and
Like, is it on a server in the line?
Yes.
If we were setting up a real line here,
Yeah,
would it be on, a rack mount server in the facility?
it would be on a separate computer somewhere so there's different levels that you can buy with Cognex. And so I'm gonna open up the Cognex site real quick, because I think this is, let's see here. Where is it? There we go. So if you go to the Cognex site, and you can even type in deep learning. So this is where you can learn a lot about their deep learning stuff. And I'll be honest, this is new technology to me even. I don't teach this at Dunwoody. But they talk all about this AI-based system, make critical decisions such as defect detection, all kinds of different stuff here. And they talk about their deep learning tools. So you can get into here and see all kinds of cool stuff. Honestly, I don't even know. Red analyze tool and green classify. I don't even know what some of these things are right now, but
what we were looking at before, that would be intended to run on some kind of computer at the site, maybe with multiple cameras streaming into it potentially, right?
pretty typical for what I just did with like the bottle example.
Yeah.
That camera would be installed on a PLC system. And so the PLC would think it's part of its own system and say, hey, look, I got a Cognex camera with IO on it. I can talk to this Cognex camera. The person programming the PLC would program in those inputs that they would get from the Cognex camera. So inspection result good, inspection result bad, fill low, fill high. And then the PLC would make decisions to drive outputs that then would respond to pass fail off of the camera. So really there is no separate PC required. There's no separate server required. It's a single PLC and a single camera can do all of that stuff.
So it is running at the edge, the algorithm.
See, the edge, yeah.
Right, it is running on the device.
It is running on the
camera
device
itself.
Yes, yeah, the code itself is running on the device. But when you get into some of more of these called higher level cameras, you're gonna have a separate controller that's running some of this higher level stuff. So you'll have a separate PC that might be running them. Some of these key-in systems, they actually make key-in systems that have a big, huge computer, and you can throw a ton of parts on like a bed. It'll measure all the parts, and give you a report back on all the parts. So you're not just measuring one part. You could like dump a bunch of washers, on a table, and it would measure all of them.
Wow.
And give you keyence, KEYENCE. Yeah, so that's more of a laboratory grade inspection system. If I am doing, say, on the industrial automation side, Cognex is where it's at. It's really, really good. Filling bottles, making batteries, doing something where I'm looking at every single part coming in online and making sure we don't make a bad part. So, yeah. How about questions online? Are there any questions online?
Not from here. It's good.
All right.
Good talk.
Awesome. I appreciate it. Well, I want to thank everybody for coming out. Just as a reminder, we will do a tech talk or a tour associated with the Twin Cities ISA chapter every other month. So right now is September. You can expect another email via ISA Connect, probably in early November for what our November activity will be. There's a board of directors meeting next month for the board of directors, and then we'll have another either tech talk or a field trip type tour in November. So thank you everybody for joining us, and I'm gonna go ahead and stop the recording and sign off. Thanks.
Edward,
Thank you.
going to the leadership meeting this fall?